I welcome you all in the sixth lecture on psychrometric processes. Previous five lectures were mainly focused on the various psychrometric properties and driving the relations for the same. In this particular session on psychrometric processes, we will present the psychrometry of common air conditioning processes, showing how the state of moist air is altered as the respective processes take place. We will also discuss various possible psychrometric processes in greater detail and depth. When one looks at the psychrometric chart, which is between the specific humidity and the drivable temperature, it is noticed that there are 8 possible ways along which the thermodynamic state of the moist air may be altered. Suppose the initial state of the moist air, that is unsaturated moist air, is at point number O. So there are 8 possible ways along which we can think of changing the thermodynamic state of this moist air. So there are 4 basic psychrometric processes known as sensible heating, sensible cooling, humidifying and dehumidifying. So when one moves along the path O to A, there is a change in the specific there is only a change in the drivable temperature of the moist air, and there is no change in the specific humidity. So this is known as the sensible heating of air. In the reverse manner, if one thinks of changing the thermodynamic state of moist air along the path O to B, this is simply inviting a drop in temperature of the moist air. Only the drivable temperature changes, but its specific humidity does not change. So this is known as the sensible cooling. If the vapor is added in the given sample of the moist air at its temperature, so the thermodynamic state of the air changes along the path O to C. This is known as the pure humidification. And if there is a situation in which the vapors are removed from the moist air without changing its dBT, that is drivable temperature, along the path O to D. So there is a continuous removal of the moisture content. So the omega continuously decreases, but there is no change in the dry bulb temperature of the moist air. So this is known as the dehumidification process. So basically, moving along the path O to A, O to B, O to C and O to D, these are the 4 basic psychrometric processes. Rest remaining 4 processes, that is moving along the path O to G, O to E, O to H and O to F. So if we are moving along the path O to G, so it is basically it is a combination of this, the sensible cooling and the heating. So ultimately it basically is a process along which the dBT of air decreases but its moisture content increases. So the process is known as the cooling and humidification. So this is the process O to G. If the thermodynamic state is altered along the path O to E, so there is an increase in the drivable temperature and there is a simultaneous increase in the moisture content also. So this process would be termed as the heating and humidification. So this is going to be a combination of these two processes, that is the sensible heating and pure humidification. Moving along the path O to F, this is a very popular process which is carried out during the summer season. This is nothing but the cooling and dehumidification. There is a simultaneous drop in temperature of the air and also its humidity level, that is its specific humidity is also getting reduced and the drivable temperature of the air is also getting lowered. So this is the cooling and dehumidification, which is popularly known as the summer air conditioning process. Moving along the path O to H, it basically invites that is an increase in the drivable temperature of the air and the removal of the moisture content. So this is nothing but the that is the heating and dehumidification process. So now we will discuss all these processes one by one in greater detail. Mixing of two streams of air is a common process in. As shown in figure 1, let us consider the adiabatic mixing of different quantities of air in two different states at constant pressure. So here we have shown a duct which has got two branches, and the duct is taken to be perfectly insulated. Through this first branch, a definite quantity of first air stream having dry air mass of Ma1 having specific enthalpy H1 at a dryable temperature of T1 and having a specific humidity level of omega 1. It flows through this first branch of the duct. Through the second branch of the duct, another air stream having a mass flow rate, that is Ma2, a specific enthalpy of moist air as H2, and it is at a dryable temperature of T2 and having a specific humidity of omega 2. So these two different air streams flow through these two ducts and they meet at a common point, and finally the mixture of these two air stream finally flows through the exit duct. So we can assume that the exit through this particular exit duct, the mass flow rate of the exit air stream is Ma3. Its enthalpy now becomes S3. It is now available at dryable temperature T3 and having a specific humidity level of omega 3. So for the sake of analysis, we assume that throughout this process of mixing of two air streams, the pressure does not change. The pressure through each duct, that is this branch number 1, branch number 2, and finally the exit branch, it is everywhere same. And we also assume that the Cp, that is the humid specific heat, is same for all the three streams. So what we can do here in order to analyze the mixing of two air streams here, we can first think of making the, that is, dry air mass balance. Because the mass of the dry air which flows through this first branch and the mass of the dry air which flows through the second branch, it does not change. So finally these two dry air masses get mixed and ultimately they leave through the system. So Ma1 plus Ma2 is going to be Ma3. So this is the equation number 1. When we make the moisture balance, because we are assuming that this duct is made up of some material which is impervious and it is assumed to be perfectly insulated also, so moisture is not going anywhere, it will remain into the system. So whatever be the moisture content of first air stream, moisture content of the second air stream, so these two moisture content get mixed and finally leave the system in the exit air stream. So mass of the water vapor which is present in the first air stream, mass of the water vapor which is present in the second air stream, they mix together and finally they become the mass of the water vapor in the leaving air system. So MV1, as we know that we can always express this mass of the water vapor in the first air stream in terms of the mass of the dry air and its specific humidity. So MV1 can be expressed as Ma1 into omega 1, where omega 1 is the specific humidity of the first air stream. Likewise, we are having the omega 2, that is the specific humidity of the second air stream multiplied by the dry air mass. So Ma2 into omega 2 is nothing but Mv2. So for this Mv3, we can simply write down Ma3 into omega 3. So this is nothing but the moisture balance, and the equation number 1 is the that is the dry air mass balance. So this is my equation number 2 for the moisture balance and equation number 1 for the dry air mass balance. So we can always change this equation number 2. So we can always replace this Ma3 using the equation number 1 as Ma1 plus Ma2. So this is going to be Ma1 plus Ma2 into omega 3, and this thing goes onto the right hand side. So this becomes Ma1 into omega 1 plus Ma2 into omega 2. So with the help of this, we determine the specific humidity of the final mixture of two air streams. So omega 3 is going to be Ma1 into omega 1 plus Ma2 into omega 2 divided by Ma3. So this is going to be equation number 3. I just request you guys to remember this particular equation, that is the final specific humidity of the mixture. With the help of this equation number 2 and this particular equation, we can always express it in terms of Ma1 and Ma2, eliminating the Ma3. So we get Ma1 into omega 3 minus omega 1 equal to Ma2 into omega 2 minus omega 3. So from here we express this, that is the difference of the two humidity two specific humidity values in terms of the ratio of the mass of the first air stream and mass of the second air stream. So it is going to be expressed as omega 2 minus omega 3 divided by omega 3 minus omega 1 is expressed as Ma1 upon Ma2. This is going to be my equation number 4. Now we can make the energy balance for the two air streams and final the mixture coming out of that particular duct. So Ma1 into H1 plus Ma2 into H2 is going to be equal to Ma3 into H3. Let it be my equation number 5. So we can express this Ma3, that is the making the dry air mass balance, as Ma1 plus Ma2 into H3 is equal to Ma1 into H1 plus Ma2 into H2. So with the help of this, we can always express it, the difference of these two enthalpies, H2 minus H3 and H3 minus H1, in terms of the ratio of the masses of two air streams, Ma1 and Ma2, and this is my equation number 6. So you would notice that the equation number 6 is quite similar to the earlier equation number 4 that we derived for the specific humidity also. So in that particular expression, we had omega 2 minus omega 3 divided by omega 3 minus omega 1 expressed in terms of Ma1 and Ma2. Now from equation number 5, we have H3 equal to Ma1 into H1 plus Ma2 H2 divided by Ma3. Suppose this is my equation number 7. Here the specific enthalpy of the moist air is nothing but Cpa into T, where Cpa is the specific heat at constant pressure. For the dry air part, it is 1.005 kilojoules per kg Kelvin. T is the dry bulb temperature of the moist air, plus omega is the specific humidity, HFG naught is the enthalpy of vaporization at 0 degrees Celsius, CPV is the specific heat at constant pressure for water vapor content, it is 1.88 kilojoules per kg Kelvin, and T is the dry bulb temperature. So H can be expressed as Cpa plus omega times Cpv into T. So dry bulb temperature has been taken common from these two terms, plus omega times Hfg naught, which can further be expressed as Cp into T plus omega times Hfg naught. So you must be remembering that Cp is nothing but the humid specific heat that we earlier talked about it. So it is going to be Cpa plus omega times Cpv. So from equation 7, we can always express this enthalpy of the mixture as Ma1 into H1 is going to be expressed in terms of this humid specific heat, dry bulb temperature, enthalpy of evaporation, and specific humidity as Cpt1 plus omega 1 Hfg naught. Likewise, we will write down the expression for H2 also. It is Cpt2 plus omega 2 into Hfg naught divided by Ma3. Now S3 can further be written down as Cp into T3 plus omega 3 into Hfg naught equal to the same right hand side in this particular equation. So from this equation, we can determine the value of the temperature of the mixture. T3 is equal to Ma1 into T1 plus Ma2 into T2 divided by Ma3 plus this whole quantity. So we notice that the second term in this particular equation is almost negligible as compared to the first term. So we can always express this T3 approximately equal to Ma1 into T1 plus Ma2 into T2 divided by Ma3. We further note from that equation number 3 and equation number 7. Equation number 3 is for the specific humidity of the mixture of two air stream, and equation number 7 is nothing but the enthalpy of the mixture of the two air streams. So omega 3 is given as Ma1 into omega 1 plus Ma2 into omega 2 divided by Ma3. Likewise, we have the similar kind of expression for the enthalpy of the mixture also, S3 equal to Ma1 into H1 plus Ma2 into H2 divided by Ma3. So from these two relations, it is concluded that the final humidity ratio and enthalpy of the mixture are the weighted average of the inlet humidity. In the expression for the temperature of the mixture, the sign of approximation has been used since an assumption has been made that the humid specific heat Cp is the same for all three streams, and Cp is given as 1.0216 kilojoules per kg Kelvin. So when we look at the equation number 4 and equation number 6 expressed for that is the specific humidity, the ratio of the specific humidity differences and the ratio of the enthalpy differences. So the right hand side of equation number 4 and equation 6 are same. So thus, if the psychrometric chart had been plotted on specific humidity versus enthalpy coordinate system, the state point for the mixture would lie on the straight line joining the two states. On the specific humidity versus dBT coordinate system, it is only approximately so. the position of the mixture state is such that it divides the straight line joining the state 1 and 2 in the inverse ratio of the masses Ma1 and Ma2 of the two dry air streams. So it is important to note from these two equations, equation number 4 and equation number 6, that the psychrometric state of the first air stream, psychrometric state of the second air stream, and the final mixtures psychrometric state, all these three psychrometric states, they lie on the same straight line, and ultimately the difference of this 1 3 and 2 3, it basically divides this whole line into the inverse ratio of the masses, that is Ma1 and Ma2. So we noticed that the mixing of two air streams is quite a common process in air conditioning. In summer air conditioning system, the room air is mixed with the cold and dehumidified air coming from the air conditioner, and in the winter air conditioning system, the room air is mixed with the heated and humid air coming from the air conditioner. So during the summer season, the requirement is basically of the cooling and dehumidification type. There is a room which is required to be maintained at 25 degrees Celsius, whereas in the absence of air conditioning, the room would be maintained at 32 degrees Celsius. When the outdoor conditions are quite harsh, ambient is available, that is TO stands for the outdoor temperature. It is taken to be 42 degrees Celsius. So my air conditioning unit, it basically takes in the air from the ambient at 42 degrees Celsius. It air conditions it, and it supplies the conditioned air to the room at 16 degrees Celsius. So this conditioned air mixes with the air which is already present in the room at 25 degrees Celsius. So here we get a mixing of the two air stream. What is the one is the conditioned air being supplied from this air conditioner, and another is the that is the return or recirculated air which is already present in that particular room. During the winter season, what happens? The outdoor condition is ambient temperature is 10 degrees Celsius. My requirement of maintaining the room is always at 24 degrees Celsius, whereas without the presence of this air conditioning unit, my room would be maintained at 18 degrees Celsius. So air conditioning unit, it basically takes in the air at 10 degrees Celsius, it air conditions it, and it supplies the conditioned air at 31 degrees Celsius to the room, so that the room could be maintained at 24 degrees Celsius. So at this point also we are having the mixing of two air streams, that is one conditioned air at higher temperature, and another air which is another air stream which is already present in the room at 24 degrees Celsius. So ultimately there is a mixing of the two air streams here, and also in this particular situation we are having the mixing of the two air streams.